This task is about configuring a hardware timer on the microcontroller instead of relying on the Arduino delay function for the main application timing. My implementation used TC3 to generate a 0.1 milliseconds time base. This time base is then used to pull a button at 400 Hz and control the blink period of LED1. In this video, I will explain timer calculation, show the code, compile the sketch, and demonstrate the button changing the LED blink period. The first key design decision is the timer setup. I selected TC3 in 16-bit match frequency mode. The Arduino SAMD core provides GCLK0 from the 48 MHz clock, with a divide by 64 per scale. The timer clock becomes 750 kHz. A 0.1 millisecond tick therefore requires 75 timer cycles. Because the counter counts from 0 to the compare value inclusive, I load CC0 with 74. This gives an exact 0.1 millisecond ticks for the selected 48 MHz clock configuration. Here, I'm showing the timer class header file. The public interface has two functions required by the task. Setup TC3 configures the chosen hardware timer, and wait TC3 accepts a time value measured in 0.1 millisecond ticks. The private sync TC3 function waits for register synchronization. This is important on the SIT329 because timer register writes are synchronized across clock domains. This implementation file is where the hardware timer registers are configured using CMSIS register access. First, PM to APB-C mask enables the APB clock for TC3. Without this, the timer peripheral would not be clocked. Next, G-clock to clock control connects generic clock generator 0 to the TCC2 and TC3 clock channel. Then Control A sets the timer to 16 bits count mode, match frequency waveform generation, and divide by 64 for scaling. Final, CC0 is loaded with 74, which is the compare value calculated earlier for a 0.1 millisecond tick. The wait function behaves like a custom delay function, but the unit is not milliseconds. This unit is 0.1 millisecond ticks. For each required tick, the function waits until the TC3 match compare 0 flag becomes set. After the match is observed, the code clears the flag by writing TC interrupt flag MC0 back to the interrupt flag register. For the application polling loop, wait TC3 is called with 25, because each tick is 0.1 milliseconds. This gives 2.5 milliseconds, which is 400 Hz. In the main application, all of the software timing values are expressed in timer ticks. Poll interval ticks is 25, so the loop waits 25 hardware ticks, or 2.5 milliseconds, before each polling cycle. The blink period starts at 20,000 ticks, which is 2 seconds. Each valid press subtracts 2,500 ticks, which is 0.25 seconds. The current version also includes a stable state debounce check. This prevents switch bounce or a floating input from causing multiple force button events. The update function is where the blink period requirement is implemented. If the current period is already at a minimum value of 0.5 seconds, the next press warps it back to 2 seconds. Otherwise, it subtracts 0.25 seconds. This serial monitor prints the selected period, which makes the video demonstration easier to verify. For the final demonstration, I uploaded a sketch. At startup, the system prints the 400 Hz button sample rates and the initial LED blink period of 2 seconds. Each time I press the button, the serial monitor prints the new blink period. The LED should blink faster after each ready press. The expected sequence is 2 seconds, 1.75 seconds, 1.5 seconds, 1.25 seconds, 1 seconds, 0.75 seconds, 0.5 seconds, and then back to 2 seconds. This demonstrates that the hardware timing is providing the polling time base and that the application logic meets the specification. Thank you.